So let's try a couple of examples. Let's revisit this flux example that we did last lesson. If you recall, last lesson we had the circle of radius 2 centered at the origin, and then we had this vector field that's plotted here as shown, and we found the net outward flux. The way we did it last lesson, let me just pull it up so you can see, was by actually doing the line integral. Here we had to parameterize the circle, and then we ended up finding f and n and ds, took the dot product, and we ended up with negative 4 pi. But because this is a closed curve, and because my vector field here has continuous partial derivatives everywhere, then I could actually have used Green's theorem instead. Instead of just integrating along the boundary, I could have integrated the divergence everywhere on the interior. So let's redo this problem that way. And again, we're going to use Green's theorem. Then this is going to be the same as the integral, if this is my region R, of the divergence. So let's find the divergence. Again, I'm going to take the partial derivative. If this is my x component and this is my y component, I'm calling that p. I'm calling the y component q and the x component p. So partial of p with respect to x plus partial of q with respect to y is going to give me 2 minus 3, which is negative 1. So in this particular vector field, my divergence everywhere is the same. It's negative 1. And that means if you think back to our video earlier, we could picture every little point here as acting like its own little sink, so that water, or it would be better to think of it as like a gas, like gas is compressing at each point. And this is helping us understand the rate. So if we actually integrate this, I'm going to get the integral of negative 1 dA over this region. Now I could, if I wanted, I could switch to polar at this point because I'm integrating over a circle. But I could also just use geometry because this is the area of the region R, and I can tell this is negative 1 times pi r squared, so pi times 2 squared, and so that's going to get me back to negative 4 pi, just like we did last time. So, and sometimes thinking of units may help. If this was, let's say, the velocity field of a gas in meters per second, then this flux is going to be meters squared per second. And the fact that it's negative is telling us that the net outward flux is negative 4 pi meters squared per second. So the gas has to be compressing because there is less gas coming out than going in. And the only way that can be happening with a gas, for example, is if it was compressing. What if C isn't centered at the origin? So let's revisit. I've now zoomed out this vector field so you can see our original circle of radius 2 would be sitting right here. But what if we shifted that and wanted to know what the net outward flux was, say, if I moved it to here in the vector field? For this particular vector field, this is my C, because the divergence is constant everywhere, because it's negative 1 at any point, then I would get the exact same calculation. My R is now this new, it's shifted over, it's right here, but I'm still going to get negative 1 dA, and so it's still just going to be negative 1 times the area of my region. In this case, it's just going to be negative 4 pi again if I keep the exact same circle of radius 2. So I get the same result in this case because the divergence is constant everywhere. If the divergence had varied depending on where I was in the vector field, then I could get different answers depending on where I moved my circle. So we'll do an example like that in a little bit, but for now I want to actually show you how we can extend this theorem to vector fields in 3D. So it turns out this same idea works, and it extends really nicely in 3D. We call it either the divergence theorem or Gauss's theorem. You'll hear it referred to as either. And what needs to hold now is I'm going to have a closed surface. So I'm just going to make it look like a sphere, but it can be any surface that's closed. And the interior of the region, let's actually, just to call it consistent, I've been calling this E, so let's call it E for the interior. And then I have some vector field. So again, you could have the velocity field of a gas that's flowing around this region. And I could ask, what's the net outward flux? Again, I'm going to need, in order to use the divergence theorem, the components have to have continuous partial derivatives everywhere inside of the surface, so throughout the region E. But if that holds, then I can find the net outward flux. And this is a capital S, this is my surface, and a lot of times if it's a closed surface, you'll see us do this around the double integral to let you know it's closed. This is going to be equal to adding up the divergence everywhere on the interior. So here I have the divergence, and now that's going to be a triple integral. But it's basically the exact same idea that we just proved in Green's theorem. I think this is a little bit more intuitive because we can think of some specific examples in real life where we've witnessed this idea. So let me help you think of why this has to be true. Let's think of the flow of a fluid, or again, we've been talking about velocity field of a gas. Then suppose I have a rigid container that's filled with gas. And if the gas starts to expand, but the container does not expand, eventually the container is going to have to explode. Somehow the gas is going to have to get out. And really that's what's being represented here in this divergence theorem, is it's connecting what's happening on the interior with what happens along the boundary. The gas expanding would mean you have positive divergence. If the divergence is positive, then that means that this triple integral will end up being positive, which means that the net outward flux has to be positive. So the gas either has to leak or the container has to explode. So it's really like a conservation of mass idea here, in the sense that whatever is happening on the inside is going to affect what's crossing the boundary. Another way we can think of this is go to the gas station, pump air into one of your car's tires. Assuming the tire is rigid and doesn't expand, what has to happen to the air inside the tire? And if you said it compresses, you are correct. And that comes directly, again, out of the divergence theorem. Pumping air into the tire would mean your net outward flux through the tire itself, like through the little boundary of the tire, is negative. And then the divergence theorem tells us if this net outward flux is negative, that this triple integral needs to be negative. And the only way that could happen is if your divergence was negative, meaning your gas is compressing. Okay, so now let's do a couple of examples of divergence theorem. Actually, we're going to do a lot of examples now.